Let us now consider this example where we have a network which is linear time invariant, and we treat this as a system. The input is this whatever voltage you give, and the response quantity is identified as the current IT. So when the switch is closed at t equals 0 in this particular network, it is observed that the current that flows into the network is given by this 4 e to the power of minus t minus 3 e to the power of minus minus 2t for t greater than 0. Of course, it goes without saying that IT is 0 for t less than 0. Given this data, you are asked to find impulse response of the network. That means if the excitation is a unit impulse, what is the corresponding output? System function taking the input voltage as the input and the resulting current as the output. C, response to an input which is e to the power of minus 4t ut. D, steady state response to an input sinusoid cos 2t. Suppose a sinusoidal voltage is given to this network, what kind of steady state current you would get in this terminals? That is the question that is asked. So all these quantities are to be obtained. Now the input is 1 volt and the output is 4 e to the power of minus t 3 e to the power of minus 2t. Therefore the input Laplace transform is 1 volt. So 1 volt is given at t equals 0 to this network. Therefore it is a step function really. V of s is 1 over s. The current in the network as the Laplace transform of this is 4 upon s plus 1 minus 3 upon s plus 2. 4 upon s plus 1 minus 3 upon s plus 2. That is the expression for the current. Therefore IFS over V of s is the system function HFS that will be obtained as, you can work this out and show that this is equal to s times s plus 5 divided by s plus 1 times s plus 2. You can show that this is the system function HFS. So that is the answer to B, which we have already obtained. If you look at this IFS can also be thought of as a step response because the input is one unit step. Therefore A of s is simply this one. So it is s plus 1 times s plus 2. So 4s minus 3s is s, 8 minus 3, 5. So this is A of s. You can see that HFS is s times A of s. That is a result which we already know. Impulse response H of t is the inverse Laplace transform of HFS. This is HFS. So HFS can be expanded by means of partial fraction expansion. So it will turn out to be 1 minus 4 over s plus 1 plus 6 over s plus 2. So if this rational function, make the partial fraction expansion of this rational function, you get this because the numerator and denominator are the same degree polynomials, s squared divided by, so the ratio of the two leading coefficients is 1, that is the first term, and then you have the residue for the pole at s equals minus 1 and the pole at s equals minus 2, it will be like this. So if you take the inverse Laplace transform of this is delta t minus 4 e to the power of minus t plus 6 e to the power of minus 2t, of course ut, you can write this 4 e to the power of minus t ut plus 6 e to the power of minus 2t ut. That is the impulse response. Now, response to e to the power of minus 4t ut. So, x of s, the input is e to the power of minus 4t, this is 1 over s plus 4. So, y of s corresponding to this is 1 over s plus 4, that is x of s, times h of s. H of s is s times s plus 5 divided by s plus 1 times s plus 2. That is the y of s. So, you make the partial fraction expansion of that. So, C continued, y of s turns out to be minus 4 upon 3 over s plus 1 plus 3 upon s plus 2 plus minus 2 upon 3 over s plus 4. That is the partial fraction expansion of this will contain 3 terms. Those are the 3 terms. So, yt will be minus 4 by 3 e to the power of minus t plus 3 e to the power of minus 2t minus 2 by 3 e to the power of minus 4t times ut. The input is e to the power of minus 4t and the output containing this term e to the power of minus 4t, this is the forced response. The forced response contains exactly the same complex frequencies as in the input. The system function has got 2 poles at minus 1 and minus 2. Corresponding to this, you have got these 2 terms e to the power of minus t, e to the power of minus 2t. So, this corresponds to this poles of x of s. So, this represents the natural response or the free response of the system. So, as we mentioned earlier, the Laplace transform theory enables us to get the total solution in one step, the free response part and the forced response part. You can apply get y of t using convolution integrals also. Now that you know ht and also you know this itself, the it itself is at, you can use the convolution and find out yt either from the impulse response or the step response, and you end up with the same result. That you can work out as an exercise. Now, it will be interesting to see whether you can get the forced response independently. Suppose you wanted only the forced response. So, the input is e to the power of minus 4t. So, the forced response of that is h s naught, where s naught is minus 4 times the input e to the power of minus 4t. So, if you substitute, this is really h minus 4 e to the power of minus 4t. We know h of s is s times s plus 5 divided by s plus 1 times s plus 4. So, when you substitute minus 4 for in this for s, you get minus 4 s plus 5 1 divided by minus 3 times minus 2. So, that will become minus times e to the power of minus 4t, that becomes minus 2 upon 3 e to the power of minus 4t. So, this is exactly what you got here. So, verification of the forced response, you can see that the forced response can be obtained by substituting s naught for s, where s naught is the complex frequency present in the input exponential signal. The last part is, what is the steady state response for cos t? Cos 2t. So, the sinusoid has an input, as input sinusoid has a frequency 2. So, hj2 equals, our h of s is s times s plus 5 divided by s plus 1 times s plus 2 with the substitution s is equal to j2. So, when you substitute s equals j2 in this, you get j2 times 5 plus j2 divided by 1 plus j2 times 2 plus j2. If you simplify this, rationalize and simplify this, this will turn out to be approximately 1.7 at an angle of 3.4 degrees. So when you substitute this J2 for S and evaluate this, the frequency response function Hj2 turns out to be 1.7 times 3.4. So if cos 2t is the input, the steady state response of that will be 1.7. This is the magnitude of the frequency response function, cos 2t plus 3.4 degrees. So this frequency response function, it tells us how the amplitude of the sinusoid, how the phase of the sinusoid are modified in the as far as the steady state response is concerned. If it is sin 2t, it would still be 1.7 cos sin 2t plus 3.4 degrees. So this is how one can use the frequency response function to evaluate the steady state response with sinusoidal driving forces. In the course of the last four lectures, we have seen how the Laplace transform method can be profitably employed to solve for the transients in networks and systems. Taking the case of network transients, to be specific, we saw that in the Laplace transform method, how the governing equations for the network in question are formed in an algebraic form, either from the transformation of the differential equation or to the transform diagram, and how the response quantities, the Laplace transforms, the response quantities can be algebraically arrived at, and therefrom through the inverse transformation how the corresponding time functions can be found out. There is no algebra involved. Furthermore, there is no calculus involved, there is only algebra that is involved. Furthermore, the initial conditions are plugged into the formation of the algebraic equations even at the very beginning itself, and no separate evaluation of the arbitrary constants is called for, as we had in the case of differential equation approach. Perhaps the greatest difficulty in the solution of by the Laplace transform method lies in finding out the inverse transformation, particularly when the denominator polynomial is of a high order. Not only we have to find the residues for the various poles, but the determination of the poles itself will become tedious if the denominator polynomial is of high order. But this is a problem which is attendant for large size problems in any method, even in the differential equation approach, and certainly the blame cannot be laid at the door of the Laplace transformation method. We have also seen how this system function can be used to evaluate the performance of a general system. The system function embodies in itself various properties pertaining to the system. We can use the system function to find out the steady state response to an exponential input by mere substitution of the corresponding complex frequency for S in the HFS. We can see how the system function can be used to find out the impulse response. We can find out how the system function can be used to find out the step response, and how the system function is almost equivalent to the frequency response function. So the system function has a number of versatile properties which we have seen, and in a general situation we can see how the system, once we know the frequency response or the impulse response or the step response, we can find out the frequency response. Conversely, if you know the frequency response over a large entire range of frequencies, there are also methods available by means of which you can find out the transient response. In other words, in linear systems, if you know the transient response, by that I mean the response to a step input or an impulse input, we can find out the frequency response for any sinusoidal input, and vice versa. There are algebraic procedures and graphical procedures available where analytical expressions cannot be found out for either the frequency response or the transient response. After having said all this, the Laplace transformation method, we must also say, has some disadvantages. Certainly, it cannot be used for systems which are either nonlinear or time varying. Even for the simple case of the product of two time functions, the corresponding Laplace transform cannot be easily found out. It involves complex convolution. For other types of nonlinearities, it may even be difficult to find the Laplace transformation. Similarly, when you have a time varying situation, the convolution integral that we have talked about cannot be used in the same form. It becomes much more complex. So for the general nonlinear and time-varying systems, Laplace transformation is almost useless. The differential equation is more fundamental, and perhaps it may furnish the only feasible method of solution in such situations, even though this may involve complicated calculations and perhaps even numerical methods for the solution. But then the differential equation method is more fundamental, and it can be used for a general situation, whereas the Laplace transform method cannot be used in such situations. So with that, we close our discussion of the application of Laplace transformation method to networks and systems, and now we will look at some problems which form an exercise on the topics that we have covered in the last 4 lectures.